In 3D video game design, there's this brilliant optimization technique called frustum culling.
Oh, yeah, that's a classic.
Right. So instead of the game engine trying to render, an entire sprawling city all at once, which would just completely melt your graphics card, it only renders the specific objects that are currently visible inside the player's camera angle.
Yeah, exactly. It forces the system to only pay the computational cost for the immediate field of view.
Exactly. And if you turn around, the buildings behind you simply vanish from active memory. It's like a perfect illusion of an infinite world, but it's powered by incredibly strict resource management.
Which is super elegant, and it's something we're currently totally failing to do in agentic software development.
Right. Which brings us to the massive bottleneck we're seeing right now. We are trying to build these AI agents that can navigate complex code bases,
Right.
interact with dozens of external services.
But instead of using something elegant like frustum culling, the standard industry approach has been to just, well, dump every single tool, API endpoint, and documentation file into the AI's context window the exact moment it boots up.
Yeah, we are handing the agent a massive warehouse of capabilities before it even knows what the task is, and it is completely paralyzing the models.
We call it context window bloat.
Yep.
And for anyone engineering autonomous systems right now, I mean, it is the absolute quickest way to degrade an LM's reasoning capabilities.
So today, we are taking a deep dive into a project that completely rethinks this architecture. We are exploring a system called Dynamic MCP Proxy.
Yeah, developed by a GitHub user named Phillips Untine37.
Right. And for those of you listening who are actively building AI workflows, or if you are just, fascinated by the systems engineering required to make AI genuinely autonomous, this is a masterclass in lazy loading and dynamic resource management.
It really is.
We've compiled the repository documentation, developer discussions, and the underlying code to really unpack exactly how this works.
What's fascinating here is the philosophy driving dynamic MCP proxy. It fundamentally flips the current standard on its head.
Okay, let's unpack this because the way it starts up is so counterintuitive.
Yeah, instead of preloading an agent with capabilities, this proxy starts the agent in a deliberately impoverished state. When the system initializes, the AI's workspace is practically empty.
Like completely barren.
Right. It has zero external tools to query databases, zero tools to read the file system, zero web scrapers, nothing.
Which makes sense if you think about it, because if you look at the raw prompt structure of a standard AI agent, every tool you give it requires a JSON schema to be injected into the system prompt.
Oh yeah, the boilerplate is huge.
Right. If you give an agent 50 tools, you are injecting thousands of tokens of pure structural boilerplate into its context window. That eats up the token budget, obviously.
Yeah, but more importantly, it dilutes the model's attention mechanism.
Exactly. It's like imagine hiring a master chef to cook you a meal, but before they even know what dish they're cooking, you just dump every single kitchen gadget, spice, and pan on their cutting board.
They wouldn't even be able to find the knife.
Right. It's paralyzing. If the AI spends 80% of its attention span just processing the instruction manuals for tools it doesn't even need, it starts hallucinating. It completely loses the thread of the actual user prompt.
That dilution is the core problem. And by starting with an empty workspace, dynamic MCP proxy preserves the model's maximum reasoning capacity for the actual logic of the task.
But I mean, a blank slate is useless if the agent can't communicate what it needs. A developer isn't going to just sit there and manually feed it tools one by one, right?
No, of course not.
Yeah.
So the proxy exposes a tiny fixed set of what it calls meta tools.
Set of tools.
Okay, these aren't tools to write code or query data. They are tools to manage other tools. And the primary bridge between the agent's empty workspace and the entire universe of capabilities is a single function.
Right, the proxy handshake.
Exactly. The mechanics of that handshake are where the system's intelligence really begins.
So how does that actually work? Like the agent realizes it has no tool, so it calls this handshake.
Yeah. When the agent receives a prompt and realizes it lacks the capabilities to execute it, it calls proxy handshake. But it doesn't just send a generic, help me request.
Right.
It is required to pass a highly structured payload to the proxy containing two really vital parameters.
Okay, let's break those down because this is where the dynamic routing actually happens.
So the first parameter the agent passes is the tech stack.
Like it's surveying its environment.
Exactly. It's declaring the terrain. It passes an array indicating, for example, that it is currently working in a Node.js environment using React for the front end and communicating with a MongoDB database.
Got it. And what's the second piece?
The second parameter is the task description. This forces the agent to distill the user's overarching goal into a localized, immediate objective.
Oh, I see. So rather than saying something vague like build a web app.
Right? The task description might be very specific, like debug the authentication middleware, failing to connect to the MongoDB instance.
Okay, so the agent packages up this tech stack and task description and fires it off to the proxy. The proxy receives this payload and now has to figure out which tools actually match that specific
Okay.
simulation.
Which is a huge routing problem.
Yeah. So to do that, it consults its master manifest, right? A file called catalog.json.
Out of the box, dynamic MCP proxy ships with a catalog containing about 45 public model context protocol servers.
And for a quick foundational note for you listening, the Model Context Protocol, or MCP, is this really cool emerging standard. It basically allows developers to package up tools and data sources into modular servers that LLMs can interact with securely.
Yeah, it's becoming the gold standard.
Yeah.
And it's not just limited to those 45 public servers either.
Right, you can add your own.
Exactly. Developers working on proprietary systems can layer in their own private infrastructure using a user.catalogue.json overlay.
So you might have standard MCP servers for GitHub and Slack, sitting right alongside highly customized internal servers for, like, your company's specific billing API.
Which means the proxy is staring at dozens of servers, potentially containing hundreds of individual tools.
So how does it filter them?
It relies heavily on metadata. Every entry in that catalog is meticulously tagged. It has a designated name, a verbose description of what it does, an array of capability tags, and its own designated tech stack alignments.
Okay, so the proxy takes the agent's handshake payload and runs a sophisticated scoring algorithm against all that metadata.
Yes, it calculates semantic relevance. It looks for keyword intersections between the agent's task description and the server descriptions.
And it maps the agent's tech stack against the server's supported technologies.
Exactly. It assigns a relevant score to every single server in the catalog based on that immediate context.
But wait, scoring is only half the battle, right? If 20 servers score moderately high, you still don't want to load all 20.
No, absolutely not.
Because then you end up right back at the context bloat problem we're trying to avoid.
Exactly. And this is where the proxy enforces a strict top K selection. It takes that ranked list of servers and aggressively truncates it.
Aggressively. I like that.
Yeah, by default, it will only select the top 5 most relevant servers. Everything else, no matter how useful it might be later, is completely ignored for now.
Oh, only 5.
Only 5. And this specific moment, the selection of those top 5 servers, is where the lazy loading actually executes.
Because up until this millisecond, all of those MCP servers in the catalog were completely dormant.
Right. They were just text entries in a JSON file. They were consuming 0 system memory, 0 CPU cycles, and taking up 0 tokens in the AI's context window.
But for those top 5 winners, the proxy initiates a live connection. And what I find particularly elegant about the system design here is that it handles those connections in 2 distinct ways, depending on the architecture of the target server.
Yeah, this part is brilliant.
It can activate them as standard input-output subprocesses, what we call Stadio, or it can connect over the network using server-sent events, or SSE.
The distinction between those 2 activation methods is totally critical for performance.
How so?
Well, when the proxy uses Stadio, it is literally spinning up a local binary or script as a child process. It communicates with that process directly through the standard input and output streams.
Which is perfect for local execution where you want absolute 0 latency.
Exactly. If the agent needs a local Python interpreter or a tool to read the local file system, spinning up a Stadio subprocess means the data transfer is basically instantaneous. There's no network overhead.
Okay, but what about SSE?
Conversely, if one of those top 5 servers is an external integration, say, a connection to a remote Jira instance or cloud vector database, the proxy will negotiate an SSE connection.
Server-sent events.
Right. They allow the proxy to maintain a persistent, lightweight lifeline to that remote API. It keeps a connection open for continuous data streaming, but without forcing the local machine to bear the compute load of running the server itself.
Okay, let me push back on this architecture for a second, though.
Sure.
Because if we are constantly evaluating contexts, spinning up local studio binaries, tearing them down, aren't we just trading context window bloat for compute latency?
Ah, I see what you mean.
Yeah, because spinning up a node process or a Python script isn't computationally free. If the agent does a handshake for every single microtask, the overhead of process creation would just grind the workflow to a halt.
That is a very valid architectural concern, and it's precisely why the top K limit and the persistent proxy state are so vital.
Okay.
The proxy doesn't tear down and rebuild the entire workspace on every single tool call. The activation is stateful.
Oh, so it keeps them around.
Exactly. Once those top 5 servers are spun up, they stay active, and their tool schemas are dynamically injected into the agent's context. The agent can then execute 5, 10, or 50 sequential steps using those activated tools without ever needing to trigger another handshake.
Okay, so the handshake is reserved for moments of like profound context switching.
Exactly. Say the agent is working along, querying the database, fixing the data layer. It has the tools it needs.
Right.
But let's say it finishes the database work and now needs to pivot to building the React front end. Suddenly, the database tools are useless, and it realizes it lacks the tools to render UI components.
That's the trigger. The agent recognizes the shift in the terrain. It formulates a brand new task description, updates the tech stack to focus on React, and calls Proxy Handshake again.
The proxy receives the new payload, reruns the scoring algorithm against the catalog, and determines a brand new set of highly relevant servers.
But wait, this introduces the next major engineering hurdle?
Budget management.
Yes. Because if the proxy just keeps loading the top 5 servers every time the agent switches contexts, the context window is going to slowly fill up anyway. It's just a delayed version of the bloat we are trying to avoid.
To prevent that cumulative bloat, dynamic MCP proxy enforces a hard limit on the total number of individual tools allowed in the agent's workspace at any given time.
Okay, what's the limit?
The default configuration caps this at 50 tools.
Interesting. So it's like a tool belt with exactly 50 slots. Once it's full, you can't add a new tool without dropping an old one.
That's a great analogy.
Yeah.
And if you think about the math there, if an average MCP server exposes maybe 8 to 10 tools, having 5 active servers puts you right around that 50 tool threshold.
So the workspace is basically always operating near capacity.
Yeah, which means when the agent triggers that new handshake for the React tools, the proxy looks at the budget and realizes that injecting 20 new UI tools will push the total well past the 50 tool limit.
It has to make room.
Exactly. If we connect this to the bigger picture, it handles this using a classic computer science caching algorithm LRU eviction.
Least recently used. It's a garbage collection strategy.
It is. The proxy is constantly monitoring the agent's actual utilization of the active tools. It tracks timestamps for every single tool call.
Okay.
When it hits that 50 tool ceiling and needs to load the new React servers, it automatically identifies the servers that have been sitting idle the longest.
So in our scenario, those would be the Postgres database tools that the agent hasn't touched in 20 minutes.
Exactly. The proxy just quietly deactivates those stale Stadio subprocesses or closes the SSE connections.
It just sweeps their JSON schemas out of the agent system prompt, instantly freeing up the token budget, and then seamlessly injects the new React tools.
This automated LRU eviction is what prevents those hallucination death spirals during long-running coding sessions.
Oh man, yeah. If you've ever watched an agent try to fix a CSS bug by accidentally invoking a Python web scraper it used an hour ago,
Wow.
why keeping the context strictly pruned to the immediate task is so critical.
Yeah, it's painful to watch. The system essentially acts as an automated memory manager, keeping the cognitive load on the LLM as low as possible.
But what if the automated garbage collection gets it wrong?
What do you mean?
Like, what if the agent knows it's going to need that database tool again in 3 steps and the LRU algorithm is about to evict it? Does the AI have any agency over its own capabilities?
It does, actually. The system is a hybrid.
Yeah.
While the LRU eviction runs as an automated safety net, the agent is also provided with manual override controls.
Oh, really?
Yeah, returning to those meta tools we discussed at the start, the agent has access to specific endpoints for state management.
Okay, so it can call proxy list active servers to audit its own current workspace. It can literally look at its own tool belt, see what is consuming the 50 tool budget, and make strategic decisions.
Exactly.
Yeah.
And if it sees a tool it knows it no longer needs, it can proactively call proxy deactivate server, passing in the specific server name to kill the process.
Wow, so it frees up space before the automated LRU even has to kick in.
Yeah, that gives the model an incredible amount of autonomy. It is dynamically summoning and dismissing its own capabilities based on its own internal reasoning about the task roadmap.
It treats tools as ephemeral utilities rather than, permanent fixtures of its identity.
Perfectly said.
Now, here's where it gets really interesting. There is one more layer to this architecture that I want to dig into, and it speaks directly to the developer experience of building these environments.
The hot plugging.
Yes, we've talked about how the proxy manages the servers it already knows about in the catalog, but a modern IDE is incredibly dynamic. Developers are constantly writing custom scripts, building new integrations, creating new MCP servers on the fly.
Right. And in a traditional setup, adding a new tool to an agent's workflow requires a hard restart.
Such a pain.
It is. You have to update the configuration file, restart the proxy server, reboot the LLM session, and completely lose the agent's current context and reasoning chain just to give it access to a new script.
But dynamic MCP proxy bypasses that entirely with hot plug support. The proxy is actually designed to watch a specific plugin's directory on the local file system.
So if you are a developer and you just finished writing a custom MCP server to query your company's proprietary telemetry data, you don't touch the configuration files.
You simply drop the new server files directly into that plugin's folder.
Yep. The proxy's file system watcher detects the new files instantly. It parses the metadata, extracts the capabilities and tech stack alignments, and registers that brand new server into the live catalog on the fly.
No restarts, no broken context chains.
None. The very next time the agent hits a roadblock and initiates a proxy handshake, that brand new telemetry server is sitting in the catalog, ready to be scored.
And if its metadata matches the agent's new task description, the proxy will dynamically spin it up and inject its tools into the agent's workspace.
It is the absolute holy grail of extensibility.
But wait, it also presents a fascinating logical puzzle for the agent.
How so?
Well, if the catalog is constantly expanding with hot-plugged plugins, how does the agent even know what is possible? If it doesn't know a tool exists, it won't know to formulate a handshake that might trigger it.
Yeah. To solve that discovery problem without triggering massive context bloat, the proxy provides another specialized meta tool called Proxy List Available Servers.
So it's essentially an endpoint for window shopping.
That is the perfect way to frame it. The agent can call this tool and pass in a filter tag to safely browse the catalog's metadata.
Oh, nice.
It gets back a lightweight list of server descriptions and capabilities.
And crucially, this read-only browsing doesn't activate anything. It doesn't spin up Stadio subprocesses, and it doesn't inject heavy tool schemas into the 50-tool budget.
Right. It just allows the agent to explore the warehouse, read the labels on the boxes, and realize, oh, hey, there's a newly added telemetry server available. I will structure my next handshake to explicitly request that.
It separates the cognitive awareness of a tool from the computational burden of loading it.
Exactly.
So what does this all mean? If we step back and look at the entire life cycle Phillips 337 has engineered here, the flow is remarkably cohesive.
It really is.
It starts with an empty workspace to preserve token limits. The agent encounters friction and fires off a handshake containing its environment and goals. The proxy scores that payload against a metadata-rich catalog, enforcing a strict top-K cutoff.
Then it lazily activates only the most relevant servers via local Stadio or remote SSE connections, injecting only those specific schemas.
And as the context evolves, the LRU eviction aggressively prunes stale tools to stay under the hard budget.
While the file system watcher quietly registers new hot plug capabilities in the background.
It is a masterclass in treating AI attention as a finite, precious resource. By ensuring the model only ever perceives the exact tools necessary for the immediate millisecond of computation, its reasoning remains sharp.
The signal-to-noise ratio is completely optimized. And for anyone building autonomous development environments, this transition from static tool loading to dynamic, just-in-time capability injection, this is going to be the dividing line.
The dividing line between what?
Between agents that get confused after 10 steps and agents that can execute complex, multi-hour engineering tasks reliably.
We've covered the mechanics of metadata scoring, the elegance of LRU eviction, and the sheer utility of hot plugging. But as we wrap up today's deep dive, I want to leave you with a thought regarding how we apply these principles outside of AI.
Oh, you mean the broader implications of lazy loading interfaces?
Exactly. We've just spent the last 15 minutes marveling at how brilliant it is for AI agents to dynamically summon and dismiss their tools to avoid cognitive overload. But if you look at our own human-facing operating systems, we do the exact opposite.
We really do.
Our desktops are littered with hundreds of icons. Our IDEs have 50 sidebars and terminal windows open simultaneously. Our phones have pages of applications aggressively demanding our attention. We have engineered our own human version of context window bloat.
Yeah, we flood our own visual and cognitive fields with capabilities we aren't actively using.
So If we have mathematically proven that an AI's reasoning degrades when it is forced to stare at tools, it doesn't currently need how long until human operating systems adopt this exact same frustum culling philosophy.
That's a wild thought.
Imagine a desktop environment that is completely, perfectly empty and only materializes the exact 3 applications you need the moment your current task demands them, quietly evicting them the second you lose focus. Something to think about the next time you find yourself digging through a crowded doc just to find a text editor. Thanks for joining us on this deep dive. We'll see you next time.